about is just about chemical and physical changes. Some questions I want you to think about as I'm covering these topics are about what a chemical change is and how we can document a chemical change. In chemistry, we like to have shorthand ways of representing things instead of large paragraphs of information. And then we'll be working our way up to figuring out if a chemical reaction can make enough product that's going to get us into stoichiometry. So in section 1 of Unit 4, we start talking about the difference between a physical and a chemical change. And to talk about those things, we got to talk about some basics that you should have already seen in other classes. Matter itself, which is what the study of chemistry is just anything that has mass and volume. All solids, liquids, and gases are going to be considered matter. There's two types of matter, two broad categories. One is a pure substance and one is a mixture. Your pure substances can be given chemical formulas. So one example of a pure substance is an element, has a chemical symbol. Another example of a pure substance is a compound, two or more elements chemically combined. It can also be given a chemical formula. Two broad types of mixtures are homogeneous, which we really just call solutions. We don't ever say homogeneous mixture in chemistry. And then heterogeneous mixture, which breaks into subcategories, but that's not a big deal at the AP level. You just need to know that homogeneous is uniform throughout. You can't see any distinguishing parts. And heterogeneous, you can see some distinct parts. So in a physical change, you're changing something about a physical property of that substance, but you're not changing its composition. A really good example would be if I take ice out of the freezer and set it out on the counter, it's going to melt and change from solid to a liquid because of the room temperature. But I didn't change it from its chemical composition. So it's H2O when it's solid, it's H2O when it's liquid. And if I took that water and boiled it and it changed into a gas, it's still H2O. So phase changes or changes in state of matter is going to be considered a physical change. Some other things are separating a mixture. Over the course of the semester, we will talk about several different ways to separate mixtures. One is chromatography, another one is distillation, another is filtration. Changing the shape of a substance, which a lot of times in chemistry problems will be referred to as deformation. So if I take a sheet of aluminum foil and I crumple it up into a ball, that is changing its shape, but I didn't make it not be aluminum. And then last is making a solution, which is a homogeneous mixture. And we make a lot of solutions in chemistry. That's going to be where we take some sort of substance, dissolve it in another substance, and that homogeneous mixture is physically combined, and we can separate those substances out if we need to by physical means. So that's a physical change. Chemical change is when I make something new. So I'm making a new composition. In a chemical change, there is bond breaking and bond forming that's going to happen. When we talk about bond breaking and bond forming, you guys are going to, throughout the semester, learn that with bond breaking, that it takes to break, TTB, and that it frees to form, FTF. So for breaking bonds, it's going to take energy to be able to break. To form bonds, it frees energy out. And later on, we'll talk about how that affects the overall reaction on if it's an endothermic or exothermic reaction. So when we're talking about chemical changes, all of the changes come from within what we call the reaction system. And so, for example, if I boil water, that water is changing, but it is coming from outside the reaction system. Water is not going to boil unless there's enough heat put into the system. Whereas in a chemical change, all the energy and everything else is going to come within what we call the reaction system. So it's typically like if I have a beaker and I combine some chemicals in the beaker, they have their own reaction. That's the reaction system. We have to look for evidences. We cannot assume a chemical reaction takes place. There's a lot of things that come into that for a chemical reaction to be able to take place. Not everything will chemically react. There's a lot of factors we're going to learn throughout this school year. Some of the evidences are production of a precipitate. A precipitate is going to be a solid that forms from a chemical reaction. A precipitate is always going to be formed from two aqueous solutions. So aqueous means that it's dissolved in water. So these are going to be formed from two solutions we've taken something, dissolved it in water. We add those two solutions to each other, and one of the products is going to be a precipitate, which is insoluble in water, and the precipitate is going to settle in the bottom of the container, and we're going to not have a precipitate before we add the two, and then once the reaction takes place, we will see the precipitate. The particles are big enough gravity can grab onto them, and that is going to settle at the bottom of a container. Precipitates take a few seconds to be able to observe because sometimes it just looks like the solution gets cloudy. Another evidence of a chemical change is color change. A lot of reactions will change color depending on the ion that is reacting. We see color change in real life when we see colors from the leaves in the fall. That's a chemical change. It's changing from chlorophyll to other pigments within that tree because the chlorophyll is dying off as the tree is going dormant. Production of light. Again, this is light that wasn't there. So when we light a Bunsen burner and we see that flame, that is a chemical change because we are producing light that was not present. Fireworks are an example of this. The light has to be coming from a chemical reaction. Change in temperature. This is getting us into endothermic, exothermic. As the temperature changes, when that takes to breaks and freeze to form happens, sometimes it's going to require more energy and be endothermic. Sometimes it will release more energy and be exothermic. We know that because the temperature changes. Again, this is within the reaction system. Production of sound. Popping sounds, like when you add vinegar to baking soda and it bubbles, or fireworks explode. Those are going to be examples of production of sound. Sound and light are both forms of energy, so it's just transferring from chemical bond energy to different forms of energy like light and sound. Production, sometimes AP questions will call this the evolution of a gas. Going back to my example, if you add vinegar and baking soda, they produce carbon dioxide, and that is going to be something that was new that wasn't there before. You have to be careful with the production of gas because boiling is changing it over into a gas, but that is not a new substance. And then things like soda, whenever you open the can or open the bottle, you're not actually producing a gas. It's just that carbon dioxide was dissolved in the soda. And when you open it, you change the pressure of the bottle to the atmospheric pressure outside of the bottle. And it looks like it just appears, but it actually was there. It's just dissolved in whenever it was at a different pressure inside the bottle. So again, you have to be careful with where is the gas coming from. Is it a new substance? And then just anytime that there's a formation of a new substance with new properties, then that is going to be a chemical change. These are the main types of chemical reactions. We have synthesis, which is sometimes referred to as composition. Synthesis is combining two or more reactants into one product. I have just generic letters for this. So you have A plus B yields AB. In synthesis, it is creating one large compound as the product. Decomposition is the opposite of a synthesis reaction. In a decomposition reaction, it's decomposing or breaking down from one compound into two or more smaller substances. Combustion is a really common one we see in AP chemistry. In combustion, you're going to start with a hydrocarbon. For my first equation, I have CX and HY. Hydrocarbons are made up of carbon and hydrogen. There's different numbers for your subscripts, so that's the reason I have just a generic X and Y. Combustion reactions have to be exposed to oxygen in order for things to burn, which is what most combustion reactions are. It has to have oxygen. And your products are going to be CO2 and H2O. Now, there is another type of combustion reaction that you will sometimes see in AP Chem. It is going to be the oxidation of a metal. And so that's what my other equation is M plus O2. And it gives you some sort of oxide. So, for example, if we were talking about the Statue of Liberty, copper reacts with oxygen and it forms that green patina that's on the outside of the Statue of Liberty, and that is considered to be a metal oxide. So that is still considered to be a combustion reaction. We don't talk about that all the time at your first level chemistry, but it's something we see in AP. Single replacement, or it could be called single displacement. In these reactions, you have an element by itself. It is going to displace another element in a compound. And so then your new products are going to be the element from the compound will go be by itself. And then it's going to form a new compound. Single replacement reactions have two different types. Sometimes the cation is the thing that is displacing, and sometimes it's the anion. So you will see different types of single displacement reactions depending on if it's the positive or negative ion switching out. And then double replacement, in this, the two compounds switch places, and you end up with two new compounds. And so, again, in this problem, A and C switched places because that's the cation. When you have a chemical formula, whatever is listed first is the positive ion. For an ionic compound, the second thing is going to be the anion, or the negative ion for an ionic compound. So A and C were both your cations, and they switch places. So A was bonded to B, but then it switches and bonds with D, and then C bonds with B. When we're doing chemical reactions, sometimes it is going to just represent a physical change. And so, for example, H2O is a gas, changing to H2O as a liquid. That's just a physical change. Didn't do anything. All it did was go through the process of condensation and went from a gas to a liquid. And you can still balance those equations. They can still have coefficients in front of them, but it is still just representing a physical change. We balance equations to prove the law of conservation of mass, because we cannot create nor destroy mass. So we have to have an equal number of mass on our reactants and our products, and we do that by adding in coefficients to balance. You're going to see these letters to represent equations. In AP Chemistry, the state of matter is really important for a lot of things we do throughout the year. So most of our chemical reactions are written with states of matter as well. And so G is gas, that makes sense. L is liquid, still makes sense. S is solid. And then AQ means it was dissolved in water. This means it is a homogeneous mixture or a solution. We've taken a solid, dissolved it in water, and we call it aqueous. So in these reactions, we are going to look at two different types of reactions, and we're going to balance these. As you're balancing, you can only add coefficients. You cannot change subscripts, because these substances are an actual chemical reaction that's taken place. And so when we're looking at balancing, I always look at the yields arrow, and whatever is on the left, I want to make it equal to whatever is on the right. You do it per element. So here I have 3 calciums. Over on my product side, I only have 1. Remember, this is my reactant side, my left. My product side is my right. We don't use an equal symbol because we're not making the same thing. We use this arrow to say that it's making a new substance. So we refer to this as being yields. So I have 3 calciums, 1 calcium. Over here, I have 2 phosphorus here, but I've got another phosphorus over here. And then I have 8 oxygens, because this 2 is going to distribute in and multiply inside the parentheses. So I have 8 oxygens over on this side, but there's another 4 here. So I have a total of 1 plus 2 phosphorus on the reactants. So I have 3 phosphorus on the reactants, and then I have 8 plus 4. So I have 12 oxygens on my reactants. On my product side, this 2 again also is going to distribute in. So I have 2 times 2, which is 4 for my hydrogens, 2 times 1, which is 2 for my phosphorus, and 2 times 4, which is 8 for my oxygen. Whenever I'm balancing, I typically do it in pencil so that if I make a mistake, I can start again. So I'm going to start this problem with the fact that I've got 3 calciums here and I only have 1 over here. So I'm going to start by putting a 3 in front of this. So that 3 is going to go in front of my balanced equation, and that's going to give me 3 calciums. I have 3 calciums. This now gives me 3 times my 4, because I have 2 times 2 hydrogens. So this is 3 times 4. So now I have 12 hydrogens. So I'm going to go over here and try to put a 4 in front of this. That gives me 4 times 3, so that gives me 12 hydrogens. When I put this here, I now have 6 total for my phosphorus. And now I have 4 here and 2 times 1, so I have 2 here. So I've got 6 total phosphorus on my reactant side. And then this gives me 8 times 3, so I have a total of 24 of my oxygens over on my product side. And then here I have 4 times 4, which is 16, plus another 8, which also gives me 24 oxygens on my reactant side. So this one will be balanced with 1 in front of this, a 4, and a 3. You do not have to include the 1, but I do that. It helps me whenever I'm doing stoichiometry, because you're going to be pulling these numbers for the relative number of moles from a balanced equation. This down here is a type of equation that you are going to see a lot in AP chemistry. It is called a dissolution equation, and it is where we are taking a solid and dissolving it in to water, and those ions are going to separate. In a dissolution equation, the ions separate into a cation and an anion, and you have to make sure it is equally balanced. So right now I notice that I have 1 calcium. I have 1 OH. This is called hydroxide. That's one of the polyatomic ions you probably want to memorize because we see it a lot in AP Chem. And this one, I have a subscript outside of this that means I have 2 hydroxides over here. So to balance this one, I'm going to put a 2 in front of my OH, and then this stays as 1, and this stays as 1. So in this reaction, what we're saying is if I take calcium hydroxide, if I take 1 calcium hydroxide, then every time I dissolve it, I will end up with 1 calcium ion and 2 hydroxide ions. AP loves making us draw things from the particle perspective. So these coefficients often will be used to draw out pictures of what's happening when we dissolve things. AP has us do lots of different things with balanced equations. You want to be sure that you're pretty comfortable with balancing. So that's where we're going to stop for today. With this section, it's really just about those basic types of equations. Can you balance, and can you identify if something is a physical or a chemical change?